All right, hello AP Statistics. This is 7.1, which is what is a sampling distribution? Okay. If you have a graphing calculator, have that out, have it handy. It'll make today's work a little bit more easy to work through. All right, now to help answer this question, the first thing we need to do is talk about some vocabulary. Okay, so we have parameter, we have statistic. Let's look at parameter. Parameter is a number that describes some characteristic of the population. Okay, it's usually, I'm going to write this right above it, it's usually too difficult to find. Okay, why is that? Well, populations are enormous. Okay, if you think about a US population, our census, it's difficult to collect the same piece of data, okay, from every single person that's within the United States. It's just too difficult to do. Even on a smaller scale, if you think about a state population or a city population or even population of a student body at a high school, it's hard to get a question answered or a group of questions answered from everybody within that group. Okay, so how do we accommodate to that? Well, we tried doing something called statistics. Okay, and a statistic is a number that describes some characteristic of a sample. Okay, remember a sample is a small group from a population. And again, once we get that information, that number, for example, ideally, okay, we'd like to generalize our findings to the population. And why is that? Well, because typically our population information is too difficult to find. Okay, so let's look at a couple things. Let's look at population, let's look at parameter, let's look at a sample, and let's look at statistic and see if we can organize information within a paragraph to see if we understand clearly what each of those items are. Okay, so here's our first problem. It says it is believed that 53% of all students at Perry High School are female. A random sample of 100 students at Perry High School were sampled, of which 51 were female. Describe the population, the parameter, the sample, and the statistic. Okay, so because population and parameter go hand in hand, I'm going to write those first. All right, so if I'm describing my population, basically I'm asking, who am I studying here? What am I studying? And I'm looking at Perry High School students. So that's all I'm going to write. Okay, and when I think about a parameter, that's a number, or in this case, a calculation that represents this population, and my calculation is 53%. Okay, so I'm going to say that P is equal to 0.53, and I'm going to define P below it. P is the proportion of PHS students who are female. Okay, now what we're going to do is we're going to take a sample of our population, and that will be, in this case, I'll write this out, 100 random students. Okay, so in this case we had 100 random students, okay, from PHS, okay, which is who we're going to study. And the statistic, the number that's associated with this sample is defined by 51 out of 100. So I'm going to say P is equal to 51 out of 100. That is my statistic, or 0.51. And I want to do something. I have two things that are both identified with a P. I have P is equal to 0.53. That was the proportion of PHS students who we thought from our population who are female. And then I have a P here where it's in our sample, 51 out of 100 were female. So, and what I'm going to do is this. I'm going to take my statistic, okay, and where I look at the P, I'm going to put a little caret above it, okay? And what that means is that I have a P hat. All right, so that is information that was obtained from a sample, okay? And again, it's a proportion. The proportion of, in this case, females that were, proportion of students who were female from this unique sample, okay? All right, second one says this. It says, it is said the average American high school student eats pizza 4.4 times per month with a standard deviation of 1.2. 300 American high school students were asked the number of times per month they ate pizza. Their responses provided a mean of 5.3 and a standard deviation of 1.9. And again, we're asked to describe the same four things. So let's look at population and parameter. Okay, and if we're looking at the type of person we're studying here, and it looks like we're studying just American high school students. So let's write that for population. Okay, and our parameter is going to be the mean and the standard deviation. So I'm going to describe the mean of this group with a mu, and we'll say that's 4.4. And the standard deviation, in this case, I'll use a sigma for that symbol, is 1.2. Okay, and I'll write those with a parameter. And then off to the side, I'm going to define mu as the average, and I'll abbreviate average, number of times an American high school student eats pizza per month. Okay, cool. Now, it's hard to ask every high school student across America how many times did you have pizza last month. So what we do is we will test this idea that was written off to the left through a sample. And from that sample, we will create a statistic. Okay, so from our sample, it looks like we have 300 American high school students were asked. Notice it says nothing about random, and that would seem to make sense because how do you pick random high school students in America from all the students in the United States? It'd be hard to do. So I'll just say 300 American high school students. Okay, and my statistic is basically the mean and the standard deviation I have from my sample. Okay, now, of course, like before, I'm going to symbolize this a little bit different. And instead of saying mean as mu, I'm going to say x bar instead. X bar is 5.3. And my standard deviation of S is 1.9. Okay. And I don't have to redefine for now because I think we're still talking about averages. But this would be x bar is the average, okay, average number of times a high school student, American high school student, ate pizza amongst the 300 students that were in our representative sample. Okay. Again, so while we have two means, one is a mu, one is an x bar. The mu is for the population, and the x bar is for the sample. Okay, and then sigma, of course, for the population, and S standard deviation for the sample. Cool. All right, sampling variability. If you think about what a sample is, okay, sample is just one small group from a giant population, and every sample could be a little bit different. Okay, it can vary based off, just the type of items that you coincidentally happen to pull. Okay, so not every sample will always look the same. And so we just have to understand that there may be some variability within your sample, and that's what this means. The value of statistic varies in repeated random sampling. Okay, so as you keep doing random samples of the same size, you're going to get different representations for each of those samples. Okay, not likely that you always get the same group of data every single time that you pick a random group of people from a population. Okay. Sampling distribution, okay, of a statistic is the distribution of values taken by the statistic in all possible samples of the same size from the population. Okay. In my terms, what this means is it's basically all possible samples right, of a certain size n. Of a population or from a population. Okay, so considering that you have this giant population, you're going to pick a size n, whatever it may be, and picking every single unique type of sample size n from your big group. Okay, so with that, sometimes we'll see some syntax that we want to make sure that we recognize. And if you see this big capital N with a, looks like a coordinate, for example, it says 54, just know that big capital N stands for a normal distribution. Okay, with a mean of, well, the first number is the 50. That is your mean. And the second number, of course, is your standard deviation. Okay, so just recognize that. That does appear often in this course. All right. All right, so let's go to an example. That'll be on your next slide. Okay, so here's the example we did in our class. It was a small activity. It was kind of fun. And we did something called the Olympics, okay? And it resembled the track and field, all right? And so I gave every student in the class 3 things. I gave everyone a javelin, everyone a discus, and everyone a shot put, okay? And then we went into the hallway, and we threw these 3 devices, collected data from them, and made some measurements, and recorded them on a sheet of paper, and then shared them with the class. Okay, now our javelin was a little different from what you may think of a javelin, but it was a pointy like spear, and it was actually this here. It's tough to see, but that is it's a toothpick. But that's what we threw. We went in the hallway. We threw toothpicks as far as we could in the hallway, and that represented our javelin. Our discus was not the heavy disc that you would throw in an Olympic event. It was actually just a paper plate. And we didn't throw it like a frisbee. You actually had to throw it internally with the palm of your hand on the cap of it, okay? And you had to spin it so it rotated off your fingers the proper way like a regular discus would. And finally, we had a shot put, okay? And we did not have 8 or 10 pound Olympic shots, but we did have a different type of orb that we used. And that was a different type of ball. It was a cotton ball. And we said with a cotton ball, you just had to throw it as is. You couldn't like scrunch it up or, you know, put water in or stuff like that to make it feel more dense and have it go further. You just had to throw it as is. And luckily for us, when we threw all these items in the hallway, we had tape measures, but we didn't need them because all the tiles on our ground were 1 foot in length. And so we just threw them, and we said that we would round to the nearest foot. And we also said that we would round, we would not round, but we would measure to the point where it first hits, okay? Not where it hit, rolled, and stopped, if that makes sense. So, so we were on the honor system with that, even though people worked kind of in pairs or in trios to collect data, okay? So, spent about 15 minutes to do that, and people came back with javelin scores, discus scores, and shot put scores. However, the only one that we used for today, and even though we marked it down on our paper, all 3 of them, we just worried about the shot put, okay, and just focused on that individual statistic, okay, to collect information from, okay. And every student in the class put his or her furthest shot put score up on the board, okay, for us to calculate data from. Okay, and in the end, after we had many, many people do this, we had 58 pieces of data, okay? And I asked the class this question at the bottom, said, now that we have displayed all our data, can you find our population mu and our population standard deviation amongst our 58 people? Okay, and I'm writing a capital N for that population of 58, okay? And they did that, okay? And we ended up with some work that look like this, and again, those are the numbers that represented all 58 people. Students and are listed by number just in the darker cells, and the shot put length in feet were in the lighter cells. And when we did one of our stats with all of our data and put all those light colored celled numbers in L1, we got this information. We got an average of 12.02, a standard deviation of 2.08, and then this part of our 5-number summary, I know my low is 7, so my minimum was 7. I take that back. I think my minimum is 8. No, it is 7. There we go. And our maximum is, I think, 19. Okay. Yeah, it's number 6. Person number 6 had the highest throw of 19. All right. And when I asked students to graph this, okay, all those data values on a histogram type piece, I just labeled the numbers 7 through 19 on the bottom, wrote shotput length and frequency. And when students came up to kind of mark a little square in based off their respective length of shotput throw, we ended up with something that looked like this, okay? And I asked my students, based off this histogram, could you please describe it? Okay, can you describe the distribution? And for many, they remembered back to an earlier chapter and they thought of socks. Okay, and the first thing there is shape. And so if I look at shape, yeah, that does look, I'd say look approximately normal. I know there's a big gap right here, but we'll just say it does look like it's peaking in the middle here and has lower frequencies as you move to the tails. So I'll say that the shape of the distribution of shot put throws okay, is approximately normal. Okay, and if I consider the other options, I know we have outliers, I know we have center, okay, and I know we have spread, okay. And so let me do this. Let's talk about spread, even though I'm not going really in order. With a spread of, and I'll just pick the lowest value that I have, 7, to the highest value, 19. And that may be with potential outliers. We'll talk about that in a second. Okay, if I was not including outliers, I would just say 7 to 15, but we don't know if they're outliers yet. The center, we actually showed in a previous slide. Okay, with the 5-number summary, it was actually at 12. Okay, so with the center of 12. Okay, and we'll see if we have any outliers. Now, I'm just going to go back a couple slides just so you can see. And you can see the center of the median is 12. We just talked about that. Q1 was 11 and Q3 is 13. So based off of those two items, I can create an outlier test. And I'm going to do that in the top left-hand corner here. I'm going to say Q1 is 11 and Q3 is 13. So my interquartile range, which is Q3 minus Q1, is 13 minus 11, which is 2. And what do we do with that too? We always take that and we need to multiply it by 1.5. Okay, so I'll do that. I'll say 1.5 times the interquartile range is, well, it's 1.5 times 2, which is 3. Okay, and so I will take Q1 and subtract 3. And I'll take Q3 and I will add 3. Okay, so Q1 is 11 minus 3 is 8, and Q3 is 13 plus 3 is 16. And for some people, they call that the lower fence and the upper fence, meaning is there any values lower than 8 within my data? And if you look, yeah, we do have a value lower. 7 is lower. So since 8 is, that's a capital, that's a cursive S, is the lower fence. Okay, that means that 7 is an outlier. Okay. And 16 is the upper fence. Okay, so 17 and 18, sorry, 18 and 19 are outliers. Okay, and we are done. Okay, so this is for my population. This is where all the students that that I had that were able to input data during that respective time. And so again, I'll say that my capital N is 58, and that's just how it looked. Okay. All right, now from that population of 58, what we're going to do is we're going to pick samples of size 4. Okay, and so I'm going to write this little n is equal to 4 in the top left. And everybody's going to pick a sample of size 4 using their random digit generator, their graphing calculator, including me. And I'm going to show you how I'm going to do this to start off. The first thing I want to make sure is that everybody has a unique starting spot. Okay, so that if we're all turning our calculators on after a cleared memory moment, we don't all get the same random 4 numbers, if that makes sense. So here's what I do. I've asked my students to put in their birth date. And when you put in your birth date, I did my son's, for example. I just typed October 8th, 1008 in the year he was born, 2014. And then what I'm going to do is I'm going to put in this arrow. It's a arrow to the right. And I'm going to circle it to my, circle it over here. Okay, that's the store button. Okay, and then next to that is RAND. Okay, and RAND can be found by doing math and then going over to probability. And I think it's the first guy there. Okay, and you just hit it. And once you have this command, you just hit enter and you're like, okay, I just typed out my birthday. And if you did that, then you are good. Okay, it doesn't really do anything else beyond that. Just kind of set your calculator up for a starting position as you start to pick random digits. Okay, now I told you before that there were 58 people who threw a shot put and gave us a piece of data for that. And I need to randomly pick 4. Okay, so what I'm going to do, and I'll write this above my second screen, I'm going to hit random integer. And the way I get there is by doing math. Okay, you're going to scroll over to probability. And then you're going to go to 5, which is rand int. Okay, and the lowest number was person number 1, who was assigned some score, who actually has some score. And then the highest person was assigned number, sorry, not the highest person, the highest person title, if that makes sense, was person student number 58. And they weren't in order from lowest to highest. It was just how they are arranged as they wrote them on the board. And I'm just going to hit 1 time each. And when I did my first calculation, and yours will probably be different, I got a 9. Okay, and that's student number 9. Okay, that's not 9 feet of a shot put throw. That's student number 9. And I want to find his or her respective shot put throw in just a moment. Okay. And then I'm going to do it 3 more times because, again, as I wrote in the top left up here, I need n equals 4. And so when I hit enter 3 more times, I got another number, 13, I got 32, and I got 34. So these are my 4. I wanted unique numbers. I don't want the same shot put thrower represented twice or 3 times or even 4 times within my random digits. Okay, so make sure that all 4 of these are different. Okay, and then what I'm going to do is I'm going to look on that chart and I'm going to circle. Let's see, here's 9. Okay, student number 9 had an 11-foot throw, so I'm going to write that up in the top left-hand corner, 11. Okay, my next student was 13. That person had a 12-foot throw. My next person was 32. That person had a 12-foot throw also. Okay, and my last one also was a 12-foot throw because he was number 34, or she was. Okay, I'm going to average those. And again, I circled these 4 based off the 4 that I had right here. I'm going to circle this real big. Okay, and this is an average, but this is an average of a sample. Okay, so I'm going to call this X bar. Okay, and what do I get when I do all that math? It looks like it's 47 over 4, which I think is 11.75. Okay, in all my students, all 58 of them also did the same thing. Okay, now likely they had different numbers like I had here. They didn't have the same 4 that I had, and which means that if they had 4 different students, they had 4 different lengths that they had to add up and divide by 4 as well. Okay, the fact that we were able to do this amongst our 58 students is the beginning of what we call a sampling distribution. Okay, we started to develop samples of size 4 from our population. Okay, now could we do all of them? Could we do every single group of 4 from this population? We couldn't, because if you look above here near the title, that would mean that we have 58 C4 within our population. Okay, different samples. And if you were to do all that math, okay, that's a huge number. I think it's 424,270. Okay, and so we didn't have time to figure out all 424,270 different ways to group 4 and then create averages for them. But we did do it 58 times, and we'll see what we got. Okay, first, that is our original data. Okay, what I found that with our new data, okay, we got something that looked like this. Okay, so when I think about what I had on the other side, my X bar, and I'll write it above here, my X bar was 11.75. Okay, and basically what I'm doing, and I'll do this in a different color so you can see it, I'm filling in 11.75 right here. That was my X bar, and you can see that I defined it that way. I'm doing this in blue. Okay, it says X bar is a shot put length. So this is the average shot put length of my 4. And I wrote off to the side n equals 4. And I had my 58 students or 50 other students, 7 other students, do the same thing. Okay, and these are all the respective X bars from their samples of size 4. Okay, from random digits. Okay, so based off that, I've asked a couple things. First, it says, what is the sampling distribution? We'll talk about that in a second. Okay, and it also says down here, it says calculate the mean of all the X bar values. Okay, so if I took all of these values, okay, and put them in my L2, for example, okay, that were plotted by my own students, okay, could I have an average? Okay, and what would that average be? Okay, so here's what I'm going to do. I'm going to put all these in L2, and I'm going to do a 1var stats. Okay, and here's what I found. Okay, and I put these in like a dark red here because that's the data that represents this work. Okay, over here. Okay, and notice my syntax here. It says the mean of all my little X bars. That's written correctly. The mean of all my little X bars is 12.02, and my standard deviation of my X bars is 1.2. Okay, how does that compare from the original? Well, my original, which is just a plain mu, is 12.05. You can see they're pretty dang close. Okay, and my standard deviation looks like it's about double, and we'll talk about that in just a second. Okay, all right, now typically, when I ask you to describe a distribution, I'm going to write this in a darker color so you can read it. If I say describe a distribution, okay, we did this earlier. You typically do this. You do the SOX thing. Okay, but if I say describe a sampling distribution, okay, I'm going to want something different. Okay, I'm going to want 3 things. The first, I want you to describe the shape. And you're like, well, that's not different. That was the first thing before. And you're right, okay? And I'm going to look at the shape and ask myself, is there any skewedness here? And as I look at that, I don't know if I see that. I don't think I see any skewedness. So maybe I'll write that, no skewedness. Okay, it is approximately normal. Now remember, this is just 58 different samples of size 4. Okay, we said that if you did every single sample of size 4 from your 58, you'd have close to 500,000. Okay, So if I were to do 500,000 of the red squares that would emerge from their samples of size 4, you actually would get something that looks a little bit more symmetric and approximately normal. Okay, and of course this would be much higher because you would certainly have more data values, but it would take a stronger looking shape. Okay. So, but yeah, I would say that looks approximately normal for what we have. I know there's some gaps here, but again, for 58 items for X bar, that's not too bad. Okay. All right. The second thing you need is this. You need your mean. Okay. Now here's what we can share, and you'll learn a little bit more about this when you do 7.3. But in this particular case, your mean of your population, that's this guy here, should, if you do this right, okay, be equal to the mean of your sampling distribution. And you can see that, yes, these are pretty darn close, okay? Why were they not exactly the same? Because you only had a sample of 58, okay, X bars. Had you had a sample of all 424,270, they would be perfectly the same. They'd be exactly the same, okay? But because you don't have every single representation of X bar from a sample size of 4 there, there's a little bit of error, okay? But in theory, this average of all those X bars should be equal to your population, okay? And so that is equal to 12.05, okay? Further, and this is the last thing, is you need a standard deviation. Okay, now your standard deviation goes like this, and standard deviation of a sampling distribution starts off like that. And what we need to know is, well, we created one for a sample of size 4, and we had, again, 58 of them. Had you done all 424,000 of them, 270, what that would be is the standard deviation of your population divided by the square root of n. Okay, so since it was told to us that our standard deviation of our population was 2.08, okay, and we know that my sample size amongst all our many was 4, okay, then the standard deviation of your sampling distribution, which is standard deviation of X bar, is, I think this turns out to be 1.04. Okay. Now, is this 1.04 close to 1.2? Well, sort of. You know, it's not too far off actually, but considering that again, we're supposed to have 424,000 plus representations for X bar for size n equals 4, and we only have 58. This is a pretty good representation of. Sorry, this was actually a pretty good representation of what it should be. Okay, so that 1.2 is actually pretty close to the 1.04, which we would expect. Okay, so that is a sampling distribution in a nutshell. And for some, they'll say, you know what, that doesn't look complete because again, you only have 58, you know, representations of data filled in there, and there's really a lot more. Okay, and you're right, there are. But for our example, and just showing what a sampling distribution is, this was more than proficient. Okay, last couple of things deals with some vocabulary, which should make a little bit better sense now that we've done an idea of sampling distribution. Variability of a statistic. Remember, variability is kind of like a spread, and a statistic is just a piece of data or a calculation or a number that you found from a sample. Okay, so we'll read this. It's described as the spread of its sampling distribution. Okay, larger samples have smaller spreads. Okay, so in theory, our population all have samples of size 1. That makes sense when we drew our original picture. And you can see that we had quite a strong variability. Okay, I'm going to go back just so that you can see it. Okay, when I say strong variability, it went from 7 to 19. That was a spread of, you know, so it had a range of 12. Okay. However, when we did samples of size 4, when we increased our n, okay, you can see it went from 9.5 as our lowest value to 14.5. Okay, and so that range change actually dropped to about 5. Okay. So our variability will decrease, okay? Our spread will decrease, okay, as our n gets a little bit bigger, okay? Nevertheless, you'll notice that the means were pretty much the same, okay? And when you divide it by the square root of n, then your standard deviations show some comparisons as well when you follow this formula. Okay? But again, variability of statistic is just more about the spread of your data. Okay, and the bigger your n, the more representative each sample is compared to the population, and it should get a little bit more narrow. Okay. All right. Last thing, and this will be something that's important for something a little bit later on in 7.3. It says the spread of the sampling distribution does not depend much on size of the population, as long as the population is at least 10 times the sample. Okay, so if your population is super big, okay, and all your samples are pretty small, okay, in general, it doesn't matter if your sample is size 4 or size 5, okay, size 10. If your population is 10 times any of those n's, then your distributions should look pretty much the same. Okay. All right, very good. If you have any questions, feel free to ask, okay? And I hope you have a great day. Here is your assignment from your book, and we will talk to you soon.